So a good question is to ask, how do you actually make kinetic measurements? And I know that my head is kind of blocking this graph that I'd like to show you, and I'm going to get that corrected in just a moment. But in the meantime, your experimental design, we're not going too far into experimental design, but in a simple way, you're mixing an enzyme and a substrate. Then what you're doing is you are going to be either monitoring the rate of substrate disappearance. Just a second, my stylus is being silly again. And here we go. I'll plug it back in. You're going to be either recording the rate of substrate disappearance or product formation as a function of time. So what you will do, and what you could do with that, is you're going to measure absorbance, specifically if your substrate or your product actually absorbs light at a specific wavelength. You're going to be measuring absorbance on the y-axis versus time on the x-axis. Okay, now with that, you're going to plot your initial velocity versus substrate concentration, which is this graph on the right-hand side here. We've got our product concentration. So this is our product concentration on our y-axis, and then our x-axis is our time. Okay. Now, what you are then going to do is you're going to change the substrate concentration and repeat that process. So what this graph shows me, this graph that I'm labeling B right here, what it shows me is substrate equal to 0.2 micromolar, 0.5 millimolar, which happens to be your Km, and substrate concentration equals to 1 micromolar. So the key with that is to be varying your concentration of your substrate. Now, what you'll do over the course of over the course of those different trials, what you'll be able to do is plot all that data, and what you'll notice is that your substrate, or you'll notice your enzymes kinetics and how all the product formation versus time is plotted. And so in an ideal situation, everything's going to kind of map out to be it's going to map out to this Michaelis-Menten, this Michaelis equation right here. And so one of the things that's valuable about that is it shows what is your velocity. So V is equal to V max times your substrate concentration divided by your Km plus your substrate concentration. I'm not sure why this is a typo here. This should be this should have a bracket around it because that's a concentration measure right there. What you can do with that ultimately, I'm plotting it here, is ultimately show what your substrate concentration is, your Km, when you are catalyzing your reaction at half of the maximum velocity. So that graph back there, or that equation, V equals V max times substrate concentration, let me write it out here, V equals V max times substrate concentration over Km plus substrate concentration, all plots, or all matches up to this plot right here. Now, this is valuable because one of the things that's important to understand and appreciate is that your enzyme does have kind of diminished marginal returns with respect to adding your substrate. At some point, your substrate is not going to have any impact, or the addition of more substrate is not going to have any impact on your enzyme's actual velocity, which is kind of displayed here with this graph right here. My stylus is really being a problem maker, or a troublemaker, I guess it would be. So that's what we're seeing with this graph. So when your substrate concentration is equal to your Km, when S equals Km, then effectively what we have is we can plug that into our equation. So I'm going to take this substrate concentration is equal to Km, and I'm going to plug it in here. I'm going to say, well, my substrate concentration, okay, so what I could do is just say V is equal to V max, and I'm going to substitute substrate concentration for Km. It'd be V max times Km over Km plus, well, that's again Km. So that effectively becomes V max times Km over 2Km. Well, the Km term is gone, and so then it's Vmax over 2. So when our substrate concentration is equal to our Km, we are at half of our Vmax. So with all that information, and just looking at this curve, let's say our substrate concentration is equal to 10 times our Km, 10 Km, okay? Well, plug that in. And I'm going to erase all these guys over here. Okay, now, again, I'm going to rewrite my equation. V equals V max times substrate concentration over Km plus substrate concentration. V is equal to V max, and I'm going to plug in 10 times my Km. I have not defined what my Km is. I don't care to define. I don't need to define what my Km is. Vmax times Km divided by Km plus 10 Km. That is Vmax times 10 Km divided by 11 Km. And again, we can remove those Km terms, and essentially it's 10 times your Vmax divided by 11. So what we're looking at is no matter how much you add, how much substrate you add, you're never actually going to get to your Vmax. Because if you make your substrate concentration 100 times your Km, well, it's still only going to get you to 100, or Vmax times 100 divided by 101. It gets you closer to your maximum velocity, but the maximum velocity is basically a theoretical number. So what I was saying a moment ago was that when you're, no matter how high your substrate concentration gets, you do have this saturation effect where you're not actually going to get to your Vmax based on the equation, the Michaelis-Menten equation of V equals Vmax times your substrate concentration divided by Km, because we don't have a linear relationship. This right here, this equation shows if we did have a linear relationship between our substrate concentration and our velocity, but we actually don't, because at some point you're going to saturate your enzyme with your substrate and you're going to see this sort of plateauing, or this plateau effect, or this tapering off of your reaction rate. Okay, so these kinetic parameters Km and Vmax are really essential for understanding enzymes. A nonlinear Michaelis plot or Michaelis-Menten plot should be used to calculate your Km and your Vmax. Now, a linearized double reciprocal plot is also good for analysis of two substrate data and inhibition data, but you can do that with the exact same Michaelis-Menten data. And in just a moment you'll see an example, but you'll also see we're going to do a couple of examples in our Zoom meetings where we go through our Km and our Vmax and making approximations with both a Michaelis-Menten plot as well as a linearized double reciprocal plot. This is also known as a Lineweaver-Burke plot. Okay, so enzyme efficiency is limited by its specificity. So what we can do is we can look at a relationship between our Km and our Kcat. Our Kcat is our turnover number, and our Km is that Michaelis constant. So diffusion from the active site limits the maximum value for specificity. An enzyme can gain efficiency by having high velocity or affinity for substrate. And an example of that would be catalase and acetylcholinesterase. So if we look at these two different enzymes, acetylcholinesterase and catalase, and we compare our Kcats, our Kcat for catalase is 4 times 10 to the 7th, which is crazy high, which is really a good thing because that tells you the number of substrates we can handle per second. So that tells you a little bit about the rate compared to acetylcholinesterase, which has a Kcat of 1.4 times 10 to the 4th. Okay, so it's lower. But let's look at our Kms. Remember, the smaller the Km tells you the higher affinity. So that's going to grab onto that substrate. And as soon as it grabs onto that substrate, what do we know about catalyzing the reaction? Our Kcat tells us a little bit about that. So what we're looking at here is a ratio of as soon as it gets the substrate, what does it do with it compared to, well, does it have a high affinity for that substrate? Okay, so our Km for acetylcholinesterase is 9 times 10 to the negative 5th, and our Km for catalase is 1.1 times 10 to the 0th. So ultimately what that means is we have a Kcat Km ratio for catalase that's 4 times 10 to the 7th. And so 4 times 10 to the 7th compared to our Kcat versus Km for acetylcholinesterase, which is 1.6 times 10 to the 8th. So if there was one enzyme that was better than the other, if you wanted to say better than, you could make the case that acetylcholinesterase is better, even though it's a little bit slower, because it has that higher affinity for the substrate. All right, well, we'll be continuing on discussing these topics. I hope this is helpful. Have a good one.